Lesson 13. Faraday's Law. Section 13.1. Time-varying fields. We have learned about the static electric and magnetic fields. There are the static electric field, and the static magnetic field. The magnetic field is generated by either a magnet or DC current. There are no interactions between these fields. In the remaining lessons of this course, we are going to study time-varying fields. A change in the electric field induces a magnetic field. And a change in the magnetic field induces an electric field. There are interactions between the induced fields. Electromagnetic waves are generated by these interactions. Section 13.2. Faraday's Law. A loop conductor is placed in free space. The loop is not closed, so that the terminal electrodes are extended to detect the voltage generated in the loop. A magnet is placed, so that magnetic flux lines go through the loop as shown in this figure. When the magnet is moving toward the loop, a voltage appears across the terminals. The polarity of the voltage is indicated by plus and minus signs as in this figure. When the magnet is moving away from the loop, the polarity of the voltage is reversed. When the magnet stops moving, no voltage is detected between the terminals. The voltage direction is defined as shown in this figure. When the magnet is moving away from the loop, the voltage V is positive. The effect of the extension conductors is negligible, and the loop can be considered closed. Therefore, the closed path is denoted by Cp, and S denotes the surface bounded by Cp. B is the magnetic flux density, and ds is a differential surface element. Then the magnetic flux phi, which passes through S, is given by this equation. Faraday's law states that the voltage V is equal to negative d phi dt. If the conductor has n turns, then the voltage becomes n times greater than the voltage for a single turn. The unit is volt. N phi is called the flux linkage. The polarity of V is explained as follows: if a resistor R is connected to the terminals, then a current I flows through the resistor due to the induced voltage, and the current flows along the loop. Due to this current, according to the right-hand screw rule, a magnetic field BI is generated in the direction shown in this figure. BI flows in the same direction so as to compensate the decreasing B of magnet. On the other hand, when the magnet is approaching the coil, the current direction reverses. The generated magnetic field BI opposes the increasing B. Even if there is no closed current path, the voltage opposing the change in magnetic flux phi is induced. This negative sign means that if phi is changing, then the voltage is induced to interfere the change of phi. Exercise 13.2.1. Pause the video, and answer the problem. Find the induced voltage V. The answer to exercise 13.2.1. Pause the video, and check the answer. Exercise 13.2.2. Pause the video, and answer the problem. Find the voltage V induced in the rectangle line conductor. The answer to exercise 13.2.2. The first step is to obtain the differential magnetic flux passing through the differential area LDR. According to exercise 10.1.2, the magnetic field intensity at a distance of r meters from the infinite line is given by this equation. The magnetic flux density B is perpendicular to the differential area. Thus, the differential flux d phi which passes through the differential area is given by this equation. The second step is to integrate the differential flux over r, and the total flux phi passing through the rectangular conductor is derived as shown in this equation. The final step is to apply Faraday's law. This concludes the answer to exercise 13.2.2. Exercise 13.2.3. This is your homework. Pause the video, and answer the problem. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.